Now in systems, we're going to start talking about electrical system modeling. So today I'm going to give you some review that you should have learned in EE 211. And also start to talk about how we can handle electrical systems in the Laplace domain. So first, we're going to talk about some of the elements. There's three main elements in circuits that we'll handle. Next class, we're also going to start talking about op-amps. But for now, we're going to deal with resistors, capacitors, and inductors. So if we have a resistor, we can represent the resistor with R, and in the time domain, we're ruled by Ohm's law. So our voltage across the resistor is equal to the current going through the resistor times R. In the Laplace domain, that equation looks the same. E is equal to IR, whether it's E of t or E of s, and our equations look very similar. But now, with our next element, the capacitor, capacitors in the time domain, we can say that our current across the capacitor is equal to our capacitance value C times the derivative of our voltage. So usually in this class and in M&I, I've noticed at Barron that we use E of t instead of V of t, I think just to show that when we're using voltage as an element, as opposed to so voltage as the value as opposed to the variable, and or as the unit. But I always learned that I is equal to C dV dt because I am Charlotte de Vries, so that's how I remember that one. It's not a very useful mnemonic for everyone, but I like it. So it's hard for me not to write C dV dt. But then if we continue on, we can say that our voltage is equal to 1 over C times the integral of our current with respect to time. Now, in the Laplace domain, if we have an integral, so we know that with a derivative, we multiply with s. For an integral, we're going to divide by s. So we can represent our capacitance as I of s times 1 over cs, and that is equivalent to integrating in the time domain. And finally, we have inductors. So inductors are represented by L, and we can say that our voltage is equal to L times di dt. And in the Laplace domain, that's going to be our voltage is equal to our current times Ls. So these are going to be the elements that we see in our systems. Next, we'll talk about our laws, just as we do every time we have a new type of system, we'll talk about the elements and the laws. And for our laws, we're going to have Kirchhoff's current law first. And so that says that for any node, the currents in are equal to the currents out. So we can say that that if we multiply if we have I1 and I2 going in, then I3 and I4 are going out. And I have this written in the time domain because all the currents are lowercase, but because of superposition, it's the exact same in the Laplace domain. For Kirchhoff's voltage law, we have that through any loop, the voltage drop will be equal to 0. So let's say that we have a simple loop with all three elements. It's going to have a voltage in of E in, a resistor, a capacitor, and an inductor. Now, through this loop, we're going to be able to say that there is a current going through it, and we could represent it in the time domain with this law as our voltage in minus our first voltage drop through the resistor, RIT, minus our second voltage drop through the capacitor, the integral of 1 over C times the 1 over C times the integral of I of t dt, minus the voltage drop in the inductor, L di dt. So we have a battery which adds voltage, and then we have elements which cause voltage drops. And in the time domain, it looks very complex, but we talked about how our elements looked in the Laplace domain, so let's look at this equation in the Laplace domain. We're going to have that our En is just going to be En of S minus R times I of S minus 1 over CS times I of S minus LS times I of S. So when we look at a circuit, it's going to be very easy to handle these elements if we stay in the time domain. And we're going to do that using something called impedance. So I'll start to define impedance on the next slide for you. And I think I'm also going to make a PDF of these slides so that way you can go through them quickly at your own pace. You don't have to pause the video. So impedance is a way to represent our functions by the relationship between our voltage and our current in the Laplace domain. So we can think of them as a type of transfer function, where voltage is our output and current is our input, and the impedance would be the transfer function to get from current to voltage. So the impedance of a resistor is R. The impedance of a capacitor is 1 over CS, because we have that integration going on. And the impedance of an inductor is LS. So if we want to think about analyzing a series circuit, so a series circuit is where all of our elements are in series. And if you had a bunch of resistors in series, you'd know that you can find the total resistance by adding them up. Same is going to happen when we have impedance. So we're going to be able to add up all of those impedances just as if they were fancy resistors. So we know that if a circuit is in series, that the current's going to be same across that wire. Regardless of what's there, the current will be the same for all of them. And we can just find our total impedance by adding up the impedance of every single element. So just like we would be able to add up every resistor if we had multiple resistors, now that we work with impedances, this is very powerful because we can treat each and every element as if it's a resistance, just by using the impedance instead of working in the time domain. Now, if we have a parallel circuit, then the current's going to split. So because of our node, we know that the current's going to split, but the voltage drop will be the same across those nodes. So now we will treat the impedances as if they were resistors in parallel. So 1 over our total impedance is going to be equal to the sum of 1 over each impedance individually. So in this case, 1 over our total impedance for this parallel circuit would be equal to 1 over R plus 1 over CS, which becomes CS, plus 1 over LS. We could then manipulate it to find our total impedance of that circuit so that we could have a relationship between I and E, which will allow us to analyze systems faster. So in our next class, we're going to start doing some example problems. For here, I just wanted to start us off with the notes. Thank you all very much.